Welcome back. So we've spent the last several classes trying to understand rotational motion, and I've tried to emphasize the point that the description of rotational motion is quite similar to our description of linear motion. In this way of thinking, the angle turned by a rotating object is analogous to the displacement of an object in translational motion. So a velocity is the rate of the distance traveled by the time, and the angular velocity is the rate at which an angle turns per unit time. And, of course, angular acceleration is again the change in the angular velocity, while the acceleration is the change in the velocity per unit time. So, for mass, we use moment of inertia, which is similar to the mass, but it also depends on the location of the mass with respect to the rotational axis. And in our last bit, we looked at torque, which is a rotational analog of force, and the torque is equal to the moment of inertia times the angular acceleration, just like the force is equal to the mass times acceleration. There are some differences here. The direction of the torque vector and the direction of the angular velocity vectors are a bit different, and we've learned to use the right-hand rule to find the direction of these vectors. The next concept we want to transfer from linear motion to rotational motion is momentum. You'll remember the linear momentum is the mass times velocity, and so the angular momentum, the rotational analog of the momentum, is the angular momentum, so L, and this is equal to the moment of inertia, I, times the angular velocity, omega. So remember, we find the angular velocity vector using the right-hand rule that you've hopefully practiced a bit by now. The moment of inertia is a scalar, so the direction of the angular momentum vector is the direction of the angular velocity vector. To find the direction, you grab the axis of rotation with your right hand, where your fingers wrap around the axle in the direction that it's turning, and once you've done that, then your thumb is pointing in the direction of the angular velocity. And this is also the direction of the angular momentum. So it's the same again. So the momentum vector is the same direction as the velocity vector in linear motion, and the direction of the angular momentum vector is the same as the angular velocity vector for rotational motion. In the example here, on the left, the wheel is turning counterclockwise, so you'd grab the axle that is pointing towards you, and your finger would point counterclockwise, and your thumb will point straight towards you out of the page there. On the example on the right, then you would grab the axle that is pointing up and down the page with your right hand, and then your fingers would wrap around the axle in the direction that it is turning. If you do that, you should be giving a thumbs up sign, and this is telling you that the angular momentum is pointing up. So how do you change the angular momentum? To change the linear momentum, we applied a force to an object, and that resulted in a change in the momentum. Newton's second law can be thought of as the force being equal to the change in momentum per unit time. So if a torque is applied to a spinning object, then this will change the angular momentum. This should make sense if a wheel is spinning such that the angular momentum is pointing up, and if we apply a torque that is pointing up, then the wheel will start to turn faster. If we apply a torque that is pointing down, then the wheel will slow down. Okay, so let's try an example and see how this works. So we have a wheel that is rotating, and it is suspended from a rope. So the spinning of the wheel provides an angular momentum, and the weight that is pulling the wheel down provides a torque. So let's work out what happens here. So what is the direction of the angular momentum? To find that, we need the direction of the angular velocity. That means we need to use the right-hand rule. The axle is pointing right and left, and the wheel is turning clockwise, as shown in the picture. So that means that if you grab the axle with your right hand, and your fingers wrap around clockwise, as shown, your thumb points to the right. So if the angular velocity vector is pointing to the right, then the angular momentum must also be pointing to the right. Next, we want to know the direction of the torque. This requires our second right-hand rule, the one where we point our finger along the radius vector, the middle finger points along the force, and then our thumb shows the direction of the torque. The wheel is attached to a pivot on the right, so the radius vector points from that axis to the point where the force is applied, so our pointer finger is pointing to the left. The weight force is pointing down, so our middle finger points down, and if you do that, then your thumb is pointing out of the page. So the finger points down, and if your thumb is pointing out of the page, so that means your torque vector is pointing out of the page. So what does that mean? In linear motion, a force changes the momentum, so if the force is in the same direction as the momentum, our object speeds up, and if it's in the opposite direction, then it slows down. And if the force is perpendicular to the momentum, then it causes it to turn. Well, here, the angular momentum is perpendicular to the torque, so the angular momentum is to the right, and the torque is out of the page, so that means that the angular momentum vector should turn. So the torque should cause the wheel to change its direction, and it will cause the wheel to spin around clockwise. So this is pretty surprising. So your intuition is probably that the wheel will just fall down, but if you get it spinning, then basically due to conservation of angular momentum, which we'll talk about in the next bit, it's going to stay pointing sideways, and then it will spin around in the circle just like I described. After this video, there's a Penn and Teller video showing the mighty cheese, and it shows how once you've given something a large amount of angular momentum, it's hard to change that. And it also shows the example of this with the spinning bicycle wheel that we're doing here. Okay, so the next example is of a similar sort of problem than when we had the bicycle wheel. And here we are pushing the handles and see how this affects the angular momentum. This is another problem similar to the previous one, and it's also a little unintuitive. I wish you could hold a spinning wheel and feel how it moves when you move it. It's really pretty surprising. So in any case, here we have a wheel that is spinning counterclockwise from above, and so when we use the right-hand rule, we find that the angular momentum is pointing up. Now we pull out at the top handle A and push in at the bottom handle B. So what torque did we apply? Well, if we take point A, then the radius points up, the force points out of the page, so the torque points to the right. If you take point B, then the radius points down, the force is into the page, and so once again, the torque points to the right. So the torque is to the right here. If the angular momentum is pointing up and the torque is to the right, then that means that the wheel will start to turn around clockwise. You can see that if you grab a pen or a pencil, you can have it point up the way the angular momentum vector points, and if you start to turn it, then you can see that the pen is going to turn around clockwise. Okay, so this is a little tricky, so you're going to have some questions to do, and we also have a video to show how potent angular momentum is, and next we're going to look at the conservation of angular momentum.